Hello everyone, today we're going to look at geometric series and annuities. A geometric series is the sum of the following form. We typically call it Sn, and it's a plus ar squared plus ar cubed, all the way up to a times r to the n minus 1. So notice that we have Sn and n minus 1. So the n is referring to the fact that there are n terms. And if you think of the first guy as being a times r to the 0, you have 0, 1, 2, 3, 4, 5, 6, 7, up to n minus 1. That's a total of n terms. So it's really important that you remember that this last exponent is n minus 1, not n. So we can find the sum using order of operations and adding up all of those n things, or the following. A times 1 minus r to the n all over 1 minus r. If you want to see how we get that equation, it's in the first page of the book, so feel free to look it over. I'm just not going to bother going over it here. So find the sum using both the long and the short ways. 3 plus 3 times 2 plus 3 times 2 squared plus 3 times 2 cubed plus all the way up to plus 3 times 2 to the 5th. So I just realized I'm really only missing one term here, but whatever. So if I want to do it the long way, I'm going to plug each of those things into the calculator. So 3 is 3, 3 times 2 is 6, 3 times 2 squared is 3 times 4, it's 12, 3 times 8, 3 times 16, 3 times 32. And then I add all those up, and I get 189. So that's the long way. The short way would be to plug it into the equation. So a is 3, r is 2, r is the thing that's being raised to those powers. And then remember, it's 1 minus r to the n, and this number is n minus 1. So if 5 is n minus 1, n must be 6. So I've got a 6 over here. Order of operations, don't forget that still exists. But you should also then be getting 189. So notice I've got two negatives, those will cancel, and I end up with positive. So let's try another one. 2 plus 2 times 5 plus 2 times 5 squared plus 2 times 5 cubed, all the way up to 2 times 5 to the 8th. So again, I can do it the long way, and I can do it the short way. The long way, I have 2 times 5, 2 times 25, 2 times 125, and I keep going, and this guy is 2 times 5 to the 8th. Add all of those numbers up, we get 976,562. That's a lot of work. It's a lot of putting things into your calculator, hoping you don't hit a typo, hoping you don't mess it up. Or we can do it the short way, and I forgot to close the parenthesis. So again, this guy is n minus 1, which makes n 9. So 2 is my a, 5 is my r, and n is my 9. I can plug this into my calculator. Again, be careful, you do need parentheses around your denominator if you're going to plug it in all at once. We get 2 times that nasty number divided by negative 4, and that's going to give me the same 976,562. Okay, so I want you to be aware that this is really what we're doing in the background of the annuities problems that we're going to look at. So an annuity is a series of equal payments made at equal intervals of time. Things like mortgage, rent, car payments, those are annuities. You typically make them every month, and it's the same amount of money each time. Things like your electric bill are paid at equal intervals, but it's not equal payments. Your electric bill changes month to month. Okay, so it's got to be the same payment at the same interval of time. There are 2 types of annuities. There is what's called ordinary annuity, which is where you make the payments at the end of each period, and there's annuities due, which is where you make the payment at the beginning of each period. If it doesn't specify whether the payments are at the beginning or the end, you assume ordinary annuity. You assume it's at the end of the pay period because that is what people ordinarily do. Please make use of the chart in your book. I'm going to assume you have it in front of you. It is, I believe, at the end with all the other tables. It's also collectively at the beginning of lesson 20 because it's going to have the whole thing. We're only going to be looking at the top half. So we're going to be looking at this part of our table. So we have what's called the future value and the present value. Ordinary annuity, annuity due. So again, ordinary annuity, annuity due depends on when you're paying it. Future value and present value depends on what the question's asking. But I want you to look especially at this equation. This is the geometric series. What we've done here is that A is now capital R, and what was our lowercase r is 1 plus I. And now these I's and N's and M's and T's and S's and A's are really the same that they were before with compound interest. So what we're really doing here is adding in a repeated payment. But again, this is a geometric series. We've switched our numbers around. Instead of 1 minus r over, to the end, sorry, over 1 minus r, we've just kind of flip-flopped them, which is fine because it's I did the same things to top and bottom. So it is a geometric series. It's slightly different if I've got annuity due, and then if I'm looking for the present value, it's going to be all different. So what I really want you to be able to do in this section is to be able to figure out which of these 4 equations you're using. And then I also want to make sure you can plug it into your calculator correctly. And again, that's a lot of making use of the answer button on your calculator, because you cannot round in the middle. Okay, just like with exponentials and compound interest, you cannot round in the middle. You need all of those crazy decimals. You've got to use the answer button. Or if you want to plug it into your calculator all at once, you have to be aware of order of operations. Something like here, I is a fraction. It's r over m, just like it was before, and that means I need to put it in parentheses because I need that fraction to be done before the big division sign above it. Okay, so you've got to be really, really careful about how you're plugging things into your calculator. And I really want to make sure that you are actually doing this with the video to make sure you're getting the same answers so that you know how to use it. Okay, so again, S is the future amount, R is the repeated payment, I is little r over m, little r being the interest rate, m being how often it's compounded per year, n is m times t, t being the number of years. So again, the letters are the same as they were for compound interest, except we're now including a capital R for the repeated payment. And I'll talk a little bit more about present value when I get to an example. So Sarah is investing $500 at the end of every quarter into an account paying 3% interest compounded quarterly. How much is in her account after 6 years? So one thing to note, that in order for this to make sense, how often she's inputting her money has to be the same as how often the interest is being compounded. So those are both going to be the same thing. It's always going to be quarterly and quarterly, weekly and weekly, monthly and monthly, and so forth. So you're not dealing with like 2 different M's here. So the first thing we have to decide is which of those 4 equations we're using. So it's at the end of every quarter, so it's ordinary annuity. And we want to know how much is in her account after 6 years. That's the future amount. So we're looking for ordinary annuity, solving for S, and that's the first equation, the top left. Then I'm going to plug all the numbers in. So 500 is R, 3 gives little r is 0.03. Not a very good decimal. Quarterly means M is 4. Again, there are 4 quarters in a year. T is 6, so I is r, little r over m, n is m times t, so we plug them in, and we get 500 times 1 plus 0.03 over 4 to the 4 times 6 minus 1 over 0.03 over 4. And then again, it's up to you to make sure you plug this into your calculator correctly. If you are having a hard time, if you're not getting the correct answers, please let me know so that we can figure out how you have to use your calculator. Make sure you are not using your phone's calculator, because A, you're not allowed to use it on a test in class, and B, it doesn't usually have an answer button, and that screws up things quite a bit. So you want to make sure your calculator has an answer button. So if you do it correctly, you should be getting $13,094.24. How much did she earn in interest? So before we had that interest equaled S minus P. And that's going to be the same thing here. It's going to be S minus P. But remember, this 500 is not P, it's R. So the total principal is going to be your repeated payment times how often you put it in, which would be M, times how many years you put it in for. So if I'm putting $500 into an account every quarter for 6 years, I need to multiply that 500 by M, the number of quarters in a year, and then multiply by T, the number of years. So I have my S minus 500 times 4 for quarters times 6 for years. So that's $13,094.24 minus $12,000 gives me interest of $1,094.24. So you have this extra step here in order to figure out P. Instead of investing money every quarter, what if Sarah wants to make a one-time deposit? How much should she deposit if she wants the same amount of money at the end as in the previous example? So this is a type of situation where you're looking for what's called A. So A is the present amount. It's not P though. Remember, P is R times M times T. So A is a one-time deposit that would be equal to your recurring payment. So it's not P. So again, it's not R times M times T. What we need to do is use that other equation solving for A. There are two situations where you're looking for A when you know your repeated payment. One is this situation here. Instead of doing a recurring payment, what can I deposit as a one-time deposit? Another is purchasing an annuity. You can buy an annuity, and what happens is you give the bank one chunk of money, which would be A, and then every quarter or month or week or whatever situation you have it set up for, they'll give you money back. So they'll give you the R after you've given them the A. Okay, so A's are, again, a one-time deposit to be equal to the repeated payment, or you're purchasing an annuity. Since we already found S for Sarah, we can solve this equation two different ways. We can use the annuities, and we can use compound interest. So if I use the annuities, then I'm looking at, again, solving for A, still the ordinary annuity, because it's still at the end of every quarter, and they would be using this equation. And again, you want to make sure that you're plugging your numbers into the correct spots. So again, it's the same situation as before, so R is still 500, M is still 4, T is still 6, little r, the interest rate is still 0.03. So again, we're just using the equation right below the one we used last time. And if we do that correctly, we should have $10,944.57. And again, what this means is instead of depositing $500 every quarter for 6 years, if she deposits $10,944.57, then 6 years later, she'll have the same amount she had last time. Another way to do it is compound interest. I want to find how much she should deposit. That would be the P from the compound interest formula. This is the S from the previous equation. She wants to have that same amount at the end. M is 4, T is 6, or little r is 0.03. So I'm just changing this into a lesson 18 problem, but you have to use the 13,000 from the previous example. You should be getting the same thing. It's off by a penny because we rounded here. This wasn't an exact answer, but it should be roughly the same thing. Okay. But again, we're going to focus more on using the annuity problems this time. And notice that for the annuities problem, I didn't have to use my 13,000. I didn't have to use the answer from the previous example. I just had to use the big R, the little r, the M, and the T. So let's try another one. John is investing $1,000 at the start of every month into an account with 4.5 interest compounded every month. How much is in his account after 10 years? So I look at the fact that it's the start of every month, so that tells me I want annuity due, so that's the right-hand column. I know that they're investing $1,000 every month, that's the repeated payment. The 4.5% interest tells me that little r is 0.045, that's supposed to be a decimal, 0.045. Every month tells me that M is 12. How much is in his account after 10 years? That's S. 10 years is T. So I want how much is in his account in the future. That means I'm solving for S. And again, it's annuity due, so that is the top right formula. The annuity due formulas are a little more complicated. So again, just make sure you're paying attention, make sure you're plugging things in correctly. So it should look like the following. So we've got 1,000 times 1 plus 0.045 over 12 to the power of 12 times 10 plus 1, then subtract 1, then divide by 0.045 over 12, then subtract 1. Okay, so again, be really, really careful with order of operations here. And you should be getting $151,765.07. Abby wants to purchase an annuity for the next 5 years. If she wants to get out $6,500 at the start of every year at 6% interest compounded yearly, what must she pay now? What must she pay now? That's A. 5 years is T. She wants to get out $6,500 at the start of every year. That's the repeated payment. Start of every year tells me annuity due. 6% interest tells me, that's a terrible looking R, tells me that R is 0.06. Okay, so I'm looking for A with annuity due, so that is the bottom right equation. That's the only one we haven't used yet, and that is probably the most complicated of all the equations. So again, I want you to make sure that you know where these numbers are all coming from. Every year, there is 1 year in a year, so M is 1. Okay, so that's where all these ones are coming from. And then everything else should fall right into place. And you should be getting $29,023.19. So if Abby gives the bank $29,000, then for the next 5 years, they're going to give her $6,500. How much would she have made in interest over those 5 years? So again, it is S minus P. So in this case, P is A, it's the present amount, and then S is the future amount. That, in this case, is RMT. So sometimes the RMT is the present amount, sometimes it's the future amount. It depends on what's happening first. So before, when I had that the present amount was RMT, it's because I put that money in first and then I got out a certain amount. But now I'm putting in my A and I'm getting this guy out. So it's really careful. You have to make sure you know what situation you're in. But you're always going to be doing R times M times T. It's just sometimes that's the present amount, sometimes that's the future amount. So like I said, in this case, it is the future amount, and I didn't write it in here, but you know, M is 1, so I would be multiplying this by 1, but it's $6,500 every year for 5 years, so 6,500 times 5. So she's getting out $32,500. She put in $29,023.19. So the difference, $3,476.81. Okay. Also, don't forget that if you don't remember which one's S and which one's P, just take the difference and make sure your answer is the positive difference, right? It's the bigger one minus the smaller one, because you can't have negative interest. All right, let's try another example. You deposit $250 every week into your bank account that accrues 3.5% interest weekly. Find the amount in your bank after 3 years. Okay, so first we have to decide, is it ordinary annuity or annuity due? So notice it doesn't specify whether it's the start or the end of every week, so we assume it's ordinary annuity. And again, if it doesn't say, we assume ordinary. 250 is my repeated payment, so that's capital R. Weekly, M is 52. There are 52 weeks in a year. R, 0.035. And then the 3 years is T. Find the amount in your bank after the 3 years. That's the future amount. So we're looking for S. So we've got solving for S using ordinary annuity. That's the top left, or the first equation in that little 2x2 square. And then again, just make sure you're plugging your numbers in correctly. Your equation should look like the following. You've got a bunch of 52s, and you've got a couple of 0.035s. Make sure you plug it in correctly, and you should be getting $41,106.51. Let's look at our last example. James deposits $400 at the start of every month into an account that gets 5% interest monthly. He does this every month for 7 years. You, on the other hand, wish to make a one-time deposit now and have the same amount as James after the 7 years. What must you deposit? So what must I deposit? That's A. It's the start of every month, so that's annuity due. So I know I'm looking for A with annuity due. That's the bottom right, or the fourth or the last equation in our little matrix of equations. So we go to plug everything in. I've got 5%, so that's 0.05 for little r. Monthly, so M is 12. 7 years, T is 7. $400 is my repeated payment. So you gotta plug that all into that lovely equation. Again, be really careful about plugging it in. And you should be getting $28,418.65. And again, what that means is that James deposits $400 at the start of every month for 7 years. You deposit $28,418.65 once. After those 7 years, you and James both have the same amount in your account, assuming, of course, you didn't add anything else in or you didn't take anything else out. Okay. The next part of this question is, how much would James make in interest? So in order to find out how much James makes in interest, I need to know his S and his P. So his P, his present amount, is going to be the R times M times T. He's putting in $400 every month for 7 years. So 400 times 12 times 7. What he gets out is S, which we haven't found yet. So I need to figure out S using the same equations as before. It's the start of every month, so it's annuity due. But now I need to find his future amount. So I'm going to use that equation. And again, the other letters are still the same. T is still 7, little r is still 0.05, capital R is 400, M is 12. And that should be $40,298.68. So again, the interest will be that number minus the 400 times 12 times 7 that we talked about earlier for P. So going to be 40,298.68 minus 33,600, which gives us an interest of $6,698.68. So a couple of things to note. James ends up putting in $33,600 altogether. You ended up putting in $28,418.65. At the end of those 7 years, you both made this amount. James put in more, which means you made more in interest. Right? If I wanted to subtract these two, your interest is, fix that as, $11,880.03. So you, making your one-time deposit, make more money in interest altogether, but you have to put more in right away. James is only putting in $400 every month, but he ends up with less interest because you've been making interest on all of your money the whole time. James has only been making interest on that first $400 the whole time. Okay? So make sure you read the book, try out the homework problems, and let me know if you have any questions. Thanks.